Well, hello everyone. Welcome. It's Professor Quark. I'm glad to be back this year, even though I didn't actually have to go anywhere to come and be with you. Just set up in my playroom here. I've got a bunch of science experiments to show you today at the Science of Circus for the 2020 Virtual Dark Sky Festival that Taubes puts on this fantastic astronomy and science festival every year. And I'm honored that they invited me back again this year. We've got lots of interesting science topics to get to today. I think the thing I want to start with is something you may have seen before. I have here in front of me a clear container and just a string of beads. These beads are the kind that you might put on your Christmas tree or decorate for a party. The thing about them is I want them to show you something interesting about the way that gravity works. So gravity is a force we feel. It's the force that stops you from just floating up into outer space when you jump up. If you jump up, you don't stay up unless you've got some a rocket or something strapped to you. Usually you jump up, you fall back down. There's some force attracting you back to the surface of the earth. Well, that's true of the beads in this jar. They are attracted to the earth by the force of gravity, and so they're just sitting in the jar there. But something quite interesting happens when you take them and you let them start to fall out. Well, that's a lot of beads. So you might have seen that before if you've come to one of my shows before. And I've been thinking about it this year, and I've been thinking, so that's kind of cool. The beads self-siphon. What does that mean? Well, ask your dad what siphoning gas is. Or your mom. Your mom's probably done it too. She's quite a capable lady. When a liquid, and these beads aren't a liquid, but they behave like a liquid for the purpose of our experiment. When a liquid is in a container, it tends to stay at the bottom of the container, except when the liquid is siphoned out. So notice that I'm going to let a little bit of this liquid, it's really beads, but we're pretending it's a liquid, come out of the jar. And I want to stop it. It's not easy to stop it. Once the process gets started, siphoning that is, it doesn't stop. It will draw all of the material that's in the container out and into some other container. So, all right, let's do that. There's another container. Let's see if we can. Siphon from one to the other. Oh, you bet we can. All right, okay, nothing to see here. Oh, that was nearly a disaster. I wonder, is it possible to siphon them out of this? That's pretty high. Do you see? See, look there. See the beads coming up? All the way up. They have to travel. Every bead has to travel up this far in order to be siphoned out of this taller jar. I wonder, can we do that? Well, let's try. Apparently not. Now, if you've seen me do this before, you'll know that it actually is important that you give the beads enough room to siphon out of the jar. Oh, I'm going to have to fix these up. Give me a sec. Put them in all jumbled. There we are. Come on, you can do it, beads. That's mad. Ooh. So that got me thinking, guys, if we can do it, if we can make the beads actually go up that far, that's 6, 7, 8, maybe 9 inches, that maybe we can make them go up this far. Should we try? All right. First of all, we got to put them in. So these beads are siphoning out. That's the word that we're using. That's the scientific word. It means to be drawn out under the force of gravity from where you're comfortable sitting. Well, do you guys think we're going to be able to siphon out of this jar? That's a lot of beads. All right, here we go. Nearly there. Well, if you've watched the last 2 demonstrations, you'll know that this is not enough, that this isn't going to siphon. Okay? It seems that the beads on the outside need to be longer than the beads on the inside. See those beads inside there? They're this long, but the beads on the outside need to be longer. So what if we were to do this? What if we were to give them more room? All right, can you see the whole jar? Oh my gosh, I can't hold the whole jar, people. Let's see what we can do. Oh, yeah. That is some serious power. That is the power to siphon that much beads up and out of this jar. Siphon is a pretty powerful force. Well, I wanted you to see just what that really looks like. Go back to this container. Let's see if there's an experiment that we can do at home with real simple ingredients. A clear container, some water, that was just water that I poured there, and some bendy straws. You've probably been wondering why these bendy straws attached together are sitting on the table beside me. It's because I'm hoping that this bendy straw, let me see, you see that better. If this bendy straw, I made it out of 3 of them, so there's the bend in one of them, there's the bend in the second one, and over there's the bend in the third one. I wonder whether we are going to be able to make the same thing happen with the water. Can we get the water to siphon out of here? Well, this is how confident I am that it's going to work. I brought a bucket. So just putting the straw in the water doesn't seem to do it. I'm going to need some help. My handy dandy tall glass container. And I'm hoping I should be able to suck up some water and fill this M-shaped bendy straw. And then let the water come out. Can you see? Can you see the water coming out of the straw there? Right there is water coming out of the straw. This is not a motor, it's not a pump. I didn't suck the water out of the glass container. I simply started the siphoning. And the siphoning only works if there's enough material on this side that it's longer than the material on that side. Remember with the beads? Well, in this case, I've set it up so that there's this amount of water on the outside where we want to siphon to. And this amount of water, it's a little bit less on the inside. It's not stopping. You know what? Let's just leave that right there where you guys can see it. Hopefully you can see that siphoning. And I want to go on to something else. I want to show you guys some unusual rolling objects. So one of the rolling objects that I first thought of was a wheel. There's a wheel. And what wheels do is they roll. They roll. If you put some stick down the middle of them, that's called the axis of the wheel. If you put a stick down the middle, then you can actually use it to roll a car down the street, or in my case, a Lego car down the street. But that is probably the most boring science that you'll ever see. It's just a wheel rolling. But I started thinking about what shape rolls like a wheel? Like what other thing other than a wheel or a tire could do that? And I thought, well, really, what this is a cylinder. These are very similar. In fact, that one doesn't even want to sit still. It wants to roll all by itself. A wheel is a cylinder and it rolls like that. Okay, excellent. What else? A wheel, a cylinder. How about one of these? Here, I'll let you guys have a good look at that. That is a special shape called an oloid. And an oloid, it turns out, rolls like a wheel. I ain't kidding. It rolls like a wheel. Then it got me thinking, all right, so we've got some shapes that roll like a wheel, but other things roll too, like a ball. So I've got here a metal ball. No reason is metal. I just think this one's kind of cute and I can see myself in it. Hi there, Professor Quark. What about that? It rolls too, but it rolls in an interesting way. It will roll any direction I want it to, not just from one end of the table to the other, but also from the back of the table to the front, across at a diagonal. This is, again, it's not one of the more interesting science experiments that you'll ever see. Rolling a ball, we call that in mathematics a sphere, right? You probably learned that in school. Then I started thinking, what else rolls like a ball? And then I found this. I'll show that to you. And you'll say, but Professor Quark, that's not a ball. No, it's not. This is an orbiform. And it turns out that an orbiform rolls like a ball. And I can't show it to you that way until I get it under a plate, and you'll see that it rolls around just like a ball. Just like that. They both work like a ball bearing. What? This thing rolls as smooth as that does. Oh, I wish you could feel that. It's so cool. It doesn't look at all like it should do that. I'll put it up here where you can see it better. It's got a point on one end. It's got a flat bottom. Well, it's sort of flat bottom, but it turns out that this, hey, are we still siphoning? It's just finishing up now. Just the last couple drops. Why did it stop siphoning? I leave that to you to decide. What has happened now that's different from before? I'll give you a hint. It's about how much material is outside of the container and how much material is inside the container. And by material, I'm talking about beads or water. So you think about why it stopped siphoning now when the amount of water is right there, right there. I wish you could see it from my angle. It is exactly level, the amount of water outside and the amount of water inside. And that is what makes a siphon work or makes a siphon not work. I'll come back to our shapes that roll, shapes that roll, a sphere and an orbiform. It doesn't make any sense though. It's got a pointy top, it's got a flat bottom, except that these are both a special kind of object, a special kind of shape. They're called solids, right? Solids because they got 3 dimensions. Solids of equal width. Wherever you measure a sphere or a ball, wherever you measure it from side to side through the middle, it's got the same width. It never changes width. And that's why no one's surprised when it rolls away from you, even on a flat surface. It's because it's the same width all over, so it rolls super easily. Guess what? So is an orbiform, a solid of equal width. And if you had it in your hand, you could take a ruler and measure its width from tip to bottom, from side to side, always through the center. It turns out that it's the same diameter. That is that width we're talking about. It's the same diameter everywhere. And as a result, it rolls like a ball. All right. Then I found this. It's a pentaorbiform. It's got a pointy top. It's got a flat bottom. But it's also got this ridge around the middle, a circular ridge. Do you see it right here? Right here? Well, you're probably not going to be surprised to find out that it too is a solid of constant width. It can, just like these other 2 shapes, the orbiform and the sphere, it can work like a ball bearing. I found all kinds of shapes that are solids of constant width, and I decided I would bring a couple of them and show them to you. I hope you enjoy those odd things, the solids of constant width. And let's take a look at how you might send a secret message to a friend. I made a secret message on this paper. I know the camera angle isn't great, but you can't see it. And you know what? That's good because it's a secret message. Going to reveal the message now. By just warming up where I put the message. Can't see it, yeah? Let's see if I can do it this way. Just warming up the paper where I wrote the secret message. All right, I can see it. You guys may not be able to see it yet, but in a second, I'll turn it so you can see my secret message. I will, you see my happy face? See if I can get an angle for it, or for you there. I made a little happy face. And how I did it was this. And you can do this too. You simply need a lemon and a Q-tip and somebody to cut the lemon for you. And it turns out that lemon juice, the stuff that squeezes out of a lemon, has a unusual property. First of all, it's got a cool name. It's a kind of chemical called a organic acid. Wow, cool, right? So organic just means from life. And I'm squeezing here. Hope that you can see me squeezing some lemon juice. If I hold that like that, you should be able to see that better. I've got some lemon juice in there. Okay, that's great. That stuff's great, great. And by great, I mean gross. Take a Q-tip, dab your lemon juice in it, and now you have a pen to make a message. So I'm doing it. I'm making another little happy face. And lemon juice is clear. You don't see, I think I can sort of satisfy you that you don't see anything there. Unless, of course, you take that organic acid and you heat it. And an organic acid that heats up turns into something called an ester. And an ester is a kind of oil. And if I'm careful, I can heat up this acid so that it becomes an oil, and then I can burn the oil before I burn the paper. Getting it, I'm getting it, I'm getting it. I think you guys maybe you might be seeing it there. Oh, it's hard because of the light. I will bring it closer to the camera once I've got it done. So my happy face is no longer invisible. It's not a secret message anymore. I'm going to suggest, by the way, that if you do this, try this, that you make sure that you get an adult to help you with the cutting of the lemon and with the working of the candle. You can put something safe on top, far away from the flame, and wait patiently, and it will warm it up. If you ask an adult to help you, you can even do this on a burner on the stove set on a very low temperature. I wonder if you can see my little message. There it is there, see? Oh, there's my happy face. And before I came on the show today, I made this one. There you are, dark sky, all done with just lemon juice, turning the organic acid of lemon juice into, using heat, into an ester, which is a kind of oil, which I then heated the oil so much that it started to change color. You know, sometimes some oil in the pan on the stove might get so hot that smoke will come off of it, and it changes color when that happens. I'm not going to suggest you try that experiment. That's a dangerous experiment. But if you've accidentally seen that happen, you may notice in the pan that the oil is no longer gold or golden colored, but that it's a dark brown. Ah, sound familiar? Like our dark sky message that we made. All right, sweet. Just for safety's sake, we're going to blow that out. And just when you thought the burning things was done, I thought, as part of a theme of stuff that you can burn, I thought maybe I ought to show you a little experiment that I learned years ago. I love to drink tea. Professor Quark loves a tasty cup of tea, and that's a pretty common kind of tea bag there. The tea is inside of a little paper bag, and I want to show you something that you can try with the paper bag. Again, this is going to involve flame and heat, and so I suggest that you get an adult to help you with this. But what I've done is I've cut the top off of the tea bag, and it turns out that if you do that, that a tea bag is really just a tube. It's just a tube, inside of which is the tea. There's the tea. And if you don't believe me that it's a tube, I'll open it up. There it is. It's just a tube. So I got to get rid of this. Got to get rid of this T. Turns out I need the plate. There we are. And so you can make a rocket. There's a rocket right there. I'm going to turn off on my overhead fan. Professor Quark was getting hot waiting for you. So I turned my fan on. There we are. So I know it doesn't look much like a rocket, but there you go. There's our tea bag, and let's watch it turn into a rocket. Now watch carefully. I'm going to set it on fire. I'm going to let it burn down all of this very thin, really, really see-through paper. And I want you to watch carefully until the burning nearly finishes. Oh, that one didn't work. It's all right. Got another one ready. That one didn't work either. I wonder why. I'll move it a little bit further forward. There it goes. There it goes. Right there. Hard for you guys to see, but that is a part of the tea bag with almost all the material burnt away, became so light that it rose up on the hot column of air created by the burning material. So the tea bag burnt and created a hotter area of air inside the tube and a cooler area of air outside the tube. And that difference in temperature made a difference in how dense the air was. Hot air tends to be less dense. It escapes, it moves fast, it's got more energy. Energy enough, in fact, to lift up a tiny bit. Let's see if I can get this and show you. Lift up a tiny bit, a tiny remaining bit of, I don't know whether that's something you can see, a little tiny remaining bit of the tea bag. Let's try one more just to see if we can't make that happen a little more dramatically for you. Tea bags are not always made of paper. Some tea bags are plastic nowadays. The paper ones are the best ones for the environment. Of course, a loose leaf tea is even better if that's something that your family does. Good for you. There you go. We'll try one more. So it's too heavy right now to rise up. And the air inside is not nearly hot enough to create a little bit of a pressure difference inside and out. It's not nearly hot enough. But I can change both of those things at once. I can make the air inside the tube hotter than outside, and I can make the tube super, super light by burning away most of its material with a controlled burn. And if we're lucky, the last bit of the tea bag should rise up. And it didn't. I'll get back to you next year on that one. We'll perfect that experiment. And in the meantime, you can try it. Make sure you get some adults to help you though, all right? All right, excellent. I thought maybe it would be a good idea if we took a look at how stars are formed. It's an astronomy festival, the Dark Sky Festival. And in fact, at night, when you go out and you look up, you do see that the sky is filled with small pinpoint twinkling lights. And we know now that those are all suns like our own. We call them stars, and they're spread around the galaxy. Nearby neighbors are a bunch of stars. And I thought it might be interesting to have a look at how stars are formed. So, and you may be saying to yourself, Professor Quark, how can you possibly demonstrate how stars are born with toothpicks and a syringe and some water? Well, watch. I'm going to take each of the toothpicks and I'm going to go right to the middle and I'm going to bend it in half. You can see maybe on the plate there how I've bent that one in half. Maybe change the angle. There you go. You can see there's one bent there in the middle. I'm going to bend 5 in the same way. Bend them right in half. Oh, that one kind of broke in half. I don't want them to break in half. I just want them to bend and still be attached. There's 3, 4. Oh, that one broke too. Toothpicks in the Northwest Territories are very, very dry. Always, always with the breaking and not the bending. There we go. I've got 5 toothpicks that I've bent in half, and I'm just going to arrange them in a particular pattern here. I'm going to stick their bent parts all to the center. There we go. And I think this is something that you guys want to see up close. So I'm going to bring it closer to the camera. And in preparation, I'm going to draw some water, as you can see, into the syringe. And I'll put this up close to the camera. There, you can see it in the camera's own reflection. And I will drop some water in the middle there. Wait for it, wait for it, wait for it, wait for it. Oh, ladies and gentlemen, I think a star is forming. Wait for it. Wait. Is it going to work? It's going to work. A little bit more, maybe. And ladies and gentlemen, we formed a star. That's a little scientific humor for you there. That's how stars are formed out of toothpicks, not the stars in the sky. That's an interesting story, how the stars in the sky are formed. It's not a story that I'm going to tell you today. That cracked me up. So I have a science experiment that I think a little bit will look like magic at first. So let's take a look at this peanut butter jar. I've emptied it out and, pardon me, I've made it so that it's the kind of peanut butter jar that's like a good friend. A good friend will always, even if they have to go home, they'll come back to visit you again. I'm clearing some space here because it's another rolling cylinder. And the rolling cylinder that I want to show you is got an interesting trick in it. Let's see, can you see that? Right, okay, here we go. I'm gonna roll this peanut butter jar, empty, don't forget, and we'll just watch and see if it behaves like a good friend. What the heck? Did you see that? Let's see if it works the other way. What did I do? I got to tell you right now. When you do science, sometimes it looks like magic. Like sometimes it looks like a magic rollback jar. It isn't, though. Also, let me just say this. Sometimes when you look at magic, there's a little bit of science in it. In this case, this is some bit of science that only looks like magic. I want to open this up and show you that that all happened because there's elastics inside and something heavy. Do you see it wibbling and wobbling there? So this jar rolls back totally against the way that gravity works, right? In fact, it rolled back against gravity. What? Well, it turns out that I was using a special property of elastics, and you've probably noticed that when you've got elastics, you have some force, you have some power. And if you don't believe me, if you've ever accidentally snapped an elastic against your finger and it hurt, that's because of the force that's in an elastic band when it gets stretched, but only when it gets stretched. So what I've done is I've created another jar here. And what I would like for you to see, I wonder if I can show you. Yeah, I can show you best here. That what's inside the jar is an elastic going through one end, an elastic going through the other end, and both of them are attached rather loosely to a roll of coins, useless coins. I know that sounds weird, useless money. No, but they are useless. They're pennies, and they used to buy stuff for us. Professor Quark's old enough to remember when you could buy a piece of bubble gum for a penny, and then it's all now it's all, Mom, I need $600 for an Xbox. Pennies are no good anymore. So instead, I thought we'd use them for a science experiment. Here's a rollback jar. This one does that same thing, only you can see it happening. Oh, I think that one has to roll up even more. Let's see how far that guy can go. There he goes. He's going back again. And inside, you can see that as I roll this, the elastics are twisting up because the weight is just lying there, not doing anything. But once you twist an elastic up, well, it's kind of like, an elastic is kind of like a chain, okay? So it's kind of an elastic when it's stretched is like this chain. See how the chain reaches right down to the table? Well, here's the thing. I'll get rid of this extra length here. When you twist an elastic, you get this. Notice that the elastic's nowhere near as long as it used to be. This chain isn't even made of elastic, but it's demonstrating what happens in elastic band normally. Normally an elastic band's sitting there all short and wiggly. Wiggly? Yeah, wiggly. But you would need like the best microscope in the world to see the wiggling, because it's all happening where the particles are, where the atoms are, where the electrons and the nuclei and all of the subatomic particles are. So normally an elastic just sitting there is all wiggly and short. And if you take it and you stretch it, it turns out you can stretch it. You just make the wiggling very angry. And you let go and it wants to do this again. So this chain is a model of the elastics in my rollback can. They're just and they're just hanging there, jiggling, jiggling, jiggling at the subatomic level, jiggling, jiggling, jiggling. And then if I stretch them, and believe it or not, all it takes to stretch an elastic is just twist it around. And I'm doing that. I'm twisting it around. I'm twisting it around. I'm twisting it around. And you can probably see inside the elastic, especially right here, you can see it. The elastic is twisting around itself very, very, very tightly in there. You see that? So that when I let it down, it wants to untwist. Why does it want to untwist? For the same reason that this chain, when it gets stretched, is just angrily vibrating and it wants to do this. It wants to be shorter. So elastics are these kind of molecules called polymer elastics or polymers in general. And they can do some really cool stuff, including making a good friend go home and then come all the way back. You can make a rollback can. All I did was tape up some pennies. You can use washers. You can use nickels, quarters, toonies, loonies, and then 2 elastics, and just make sure that they're loosely tied to the top and bottom of some sort of a container. That's the reason why I chose plastic ones. Oh, by the way, you're probably wanting to see the whole story in there. There it is. There it is. Gets twisted around. Then the elastic wants to do that jiggling, shortening thing that it does before. All right, I got one more for you. I've made a mess here, and I'm going to need some room for this one. So let me just make sure. Yeah, there we go. I got one more for you. This could go wrong. You know, I'm not afraid to try. Oh, by the way, there is your star. There it is. That's the star, how a star is born. That's a joke for your parents. Okay, you know me, I'm not afraid to try the science that's right on the edge, the stuff that maybe will or won't work. My little teabag rocket didn't work out very well today. Here's another one that might not work out, and I'm gonna have to stand back for this one. You guys are safe, you're behind the camera there. But it involves toilet paper roll. Now here's the thing, you can't use the toilet paper little insert there. You can't use it until you've used the toilet paper. Don't unroll a roll of toilet paper just to get this little tube out of the middle. What are you, a cat? But also your mom will be like, what are you, crazy? That's perfectly good toilet paper. So first of all, use the toilet paper and then get your toilet roll out. You're going to need a glass, and you're going to need that glass filled up with some water. And you're going to need a pie plate. One of those. And good idea to get a round one. But if you've got only one of those little square ones, as long as the lip's not too high on the side, it's fine. I'm going to talk to you today about inertia. We've got our water waiting for, in case this doesn't work. And now the stars of the show, eggs, ladies and gentlemen. Not hard-boiled eggs, just eggs straight out of the fridge. And Professor Quark didn't bring his. Hold on, I've got to go to the fridge of science. All right, Professor Quark has got his eggs of science from Polar Eggs, of course. Where else would you get your eggs? There we are. Let's leave those right there. So there's an egg. There's a toilet paper roll. There's a glass of water. And I need a weapon. There's my weapon, my broom of science. And I'm going to I'm going to prove to you that you can make that egg fall into that glass without touching it. Did you hear me? Going to make that egg fall into that glass without touching the egg, without touching the toilet paper roll, without touching, well, I should probably show you. I'm going to put this on top of that, just like that there. So there's our glass of water with our pie plate on top. And you guessed it, we're also going to put the toilet paper roll on top of that and put the egg on top of that. And then we're going to stand back. Because Professor Quark, without touching any of these things, is going to make that egg fall into that glass. Whenever I look at it, I think, nah, there's no way that this is a thing that you can do. But you can. I'm not going to touch it. Instead, I'm going to load up my broom with some energy. There it is. Some energy in my broom. I'm stepping on the bristles. You can't see down here. I'm stepping on the bristles and making it so that when I let go, this broom is going to go forward, tap that whole assembly, and if we're lucky, make it fall into the glass. Oh my gosh, this seems impossible. It's a long way down there. All right, here we go. Count to 3. Count down from 3, not up to 3. What was I thinking? 3, 2, 1. Egg in glass. I didn't touch it. It's awesome. And in fact, it's so good that I think that we can do this again. Only this time, let's do 3 eggs. 1, 2, 3. If I'm successful, I'll make all 3 of these eggs fall into all 3 of these glasses without touching them. Well, that's not very much water. Okay. 1, 2, 3 eggs into 3 glasses of water. This is not something that I recommend you try at home indoors. You definitely want to go outside for this one. Whoa, hello, whoa, hello. Behave yourself, people. 1, 2, it's very wobbly. 3, oh, excellent. All right. Load up my broom of science. All right, I'm not afraid. I'm not afraid. I can do it. Three, 2, 1. Ladies and gentlemen, science can be messy. It can be kind of anxiety making. It can be super fun and confusing, and it can be funny. It can be all of those things. But if you don't do it, it can't be anything for you. So do it. Get some glasses, get some eggs, get some toilet paper roll. Remember, use the toilet paper first. Remember to wash your hands. And Professor Quark says, just go out and have fun with science at this Dark Sky Festival this year, 2020, the one where we're all doing it from our homes. Thanks very much for coming to the Circus of Science and having a fun time with Professor Quark. I will see you guys again next year. Thank you. Bye-bye.